In this class, we will discuss some more important problems which is based on the fatigue loading. Okay. Now, let us understand the given problem. Okay. The problem is a cantilever beam made of cold drawn carbon steel. Okay. Cold drawn carbon steel. For that, okay, we have ultimate strength which is 550 MPa. Yield strength we have 470 MPa, and endurance limit sigma minus 1 we have 275 MPa. Of circular cross section is subjected to load which varies from minus f to 3f, which varies from minus f to 3f. So here what we need to determine? We need to determine the maximum load that the member can withstand for an infinite life. The member can withstand an infinite life using the factor of safety of 2 and the notch sensitivity is equal to 1. Notch sensitivity is equal to 1. So this is a given problem. In this problem, what we need to do? We need to determine the maximum load that can that the member can withstand for an infinite life. Here what is the load varies, which varies minus f to 3f, which varies minus f to 3f. For example, what we have? We have a cantilever beam. So you can see here, you just observe the cantilever beam. This is the nature of the problem. This is the nature of the problem. (20 mm) dia of the beam, and this length we have 125, and this length we have 150, and here diameter 15. It should be 15. And R, radius of the fillet, which is R3. And here the nature of the load is, it should be 3F. And here it should be F. For example, you can see here, this is the nature of the load F, which is counterclockwise direction. That's why we will consider negative sign. Same way you can see here, this, the nature of the load which is clockwise, we will consider positive sign. When the load is applied on this cantilever beam, cantilever beam made of cold drawn carbon steel, with the properties of ultimate stress, which is 550 MPa, and yield stress 470 MPa, and endurance limit 275 MPa. So the load which is varies from F to 3F. F to 3F. So this is a given problem. Here what we need, first let us note down the given data. First let us note down the given data. Here sigma u is equal to 550 MPa, sigma u is equal to 550 MPa, sigma y is equal to 470 MPa, sigma y, we have, and endurance limit sigma minus 1 is equal to 275 MPa, 275 MPa, and also we know the small d which is 15 mm, and capital D is equal to 20 mm. And we have radius of the fillet R is equal to 3, and factor of safety small n is equal to 2, and notch sensitivity, which is denoted by Q, is equal to 1. This is the given problem. This is a given problem. With respect, this is a given data with respect to this problem. Okay, here, okay, what is the load, okay, which varies minus F to F. Okay, this is the, okay, minus F to F. Okay, this is the given load, okay, which varies on a circular cross section. Okay, circular cross section. Here we need to consider if, okay, they will not given any condition, either you need to go for Goodman or Soderberg. Okay, you just go ahead with a Soderberg equation. Okay, note down the Soderberg equation, Soderberg criteria for bending, Soderberg criteria for bending load. Soderberg criteria for bending load, we already discussed that equation, that is K sigma minus 1 into sigma BA divided by, okay, sigma minus 1 D plus sigma BM, okay, mean stresses with respect to bending, sigma YD is equal to 1. Okay, you consider this as a equation number 1. Okay, you consider this as a equation number 1. Okay, before that, okay, before find out all these things, okay, we need to find out the stress concentration. Okay, so and also we need to note down that some of the important correction factors. Okay, so you just consider, okay, ESZ, okay, correction factor with respect to size, which is 0.85. Therefore the diameter, which is 7.5 less than D or less than 50 mm. Okay, this is a notation we already discussed in the theory class. Okay, so this is the size correction factor. Okay, and also EL is equal to 1, okay, for the bending load. If it is not given for bending load, you need to consider EL is equal to 1, and ESR is equal to 0.83, okay, 0.83 at, okay, sigma u is equal to 550 MPa. Okay, I will show you how to take this value from the design data handbook. Yesterday problem we discussed this, how to measure this. For example, if we have that figure number, okay, 5.3 from the design data handbook, okay, figure number 5.3, figure number 5.3 from design data handbook. Okay, here what we have in x axis, we have sigma u, okay, in y axis what we have ESR. Okay, I will show you that, okay, graph, how to find out that value. Okay, 1 minute. Now you can see this is the design data handbook. Okay, the page number 5.8, okay, the page number 5.8, the figure number 5.3, okay, which indicate reciprocals of stress concentration factor caused by the surface condition. Okay, so in x axis what we have a tensile strength, okay, sorry, a tensile ultimate tensile strength, okay, that is sigma u in terms of MPa, and this side we have surface factor. Okay, for the rough finish we need to consider for the rough finish. Okay, now you can see here, okay, what is the ultimate strength we have, which is 550 MPa. Now this is the 400, okay, in between 400 and 600 exactly somewhere here we need to consider 550 MPa. Okay, now we just draw one straight line, okay, we just draw one straight line, okay, with the help of scale up to rough surface, okay, rough finish. Then from this point you need to draw one more line, okay, from this point you need to draw one more, okay, horizontal line with respect to this. Okay, we'll get around, okay, we'll get around 0. Okay, we'll get around 0.83, okay, we'll get around 0.83, okay, from this graph or from this figure. Okay, this is how we can measure the surface factor with respect to this okay, problem, okay, with respect to this ultimate strength, with respect to this ultimate strength. Okay, so this is the okay, with respect to ultimate strength, this is how we can find out. This is the value, rough finish. Okay, here we'll get around 550. Okay, this is 0.83, okay, 0.83. Okay, this is how we can find the value. Next, what we need to find out, okay, we need to find out the stress concentration. Okay, as we all know that how to find out the stress concentration. Okay, to find okay k sigma minus 1 is equal to 1 plus q, okay, into k sigma minus 1. Okay, here we need to find out this and as well as this. First we will find out the k sigma. Okay, how to find k sigma? To find k sigma, what is the procedure? That we all know that d by d and r by d ratio. Okay, d by d as well as the r by d ratio with respect to this figure. Okay, with respect to this figure, what is the d by d ratio? D by d is equal to 20 by 13. Capital D is equal to capital D 20 mm. Small d is equal to 30. So small d is equal to 13 mm. Okay, small d is equal to 13 mm. Okay, if you simplify this, okay, you will get 1.538. okay, and then what is the r by d? What is the radius of the fillet? Which is 3. Okay, so 3 by 13. Okay, if you simplify this, we will get 0.23. okay, we will get 0.23. okay, so this is a d by d as well as r by d ratio from the design data handbook. Okay, refer figure. Okay, refer figure. What is the figure number? 4.21a. 4.21a for the d by d as well as r by d ratio. Okay, with respect to this condition. Okay, now I will show you this. Okay, this is the design data handbook. Okay, this is a figure number 4.21. okay, you can see here, this is a condition. Capital D we have, small d we have, r we have. Okay, so now this problem is subjected to bending. Now you can see here. Okay, here we have in x axis we have r by d, in y axis we have k sigma. Okay, so here we have d by d lines. What is the d by d? Okay, r by d we will get 0.23. okay, now you can see 0.20. somewhere here we will get 0.23. okay, you draw one line. Okay, you draw one line like this and you draw one more line like this. Somewhere here we will get the value called k sigma. Okay, likewise if you see, this is the value. Okay, this is the x axis we have r by d, y axis we have k sigma. Okay, here we have d by d. Okay, which is somewhere here what we will get. Okay, so capital D by d which is 1.5. okay, 1.53. okay, somewhere here we will get 0.23. okay, you draw one line like this and you draw one more line like this. Somewhere here we will get around 1.38. Okay, this is the procedure to find out the stress concentration. We already discussed it several times with various problems. Okay, so now if you substitute these values, okay, so where k sigma is equal to 1.38. okay, if you substitute this value into this equation, okay, this value into this equation, okay, you just find out the k sigma minus 1, that is equal to 1 plus what is the value for q? Okay, notch sensitivity which is given in the problem, that is 1. okay, so which is 1. okay, 1 plus 1 into what is the value for k sigma, which is 1.38. okay, 1.38 plus 1.38 minus 1. if you simplify this, we will get same value. K sigma minus 1 is equal to 1.38. okay, same value will get. Okay, this is a value for the stress concentration. Okay, from this what we need to do? We need to find out. Okay, next what we need to find out? We need to find out the bending. Okay, with respect to this we need to find out the maximum bending at fillet. Okay, maximum bending at fillet. Next, maximum bending at fillet, that is equal to MB max. MB max is equal to 3F. At what distance? 3F into, okay, this is the 3F force which is varied. The load which is varies 3F to minus f to 3f, okay, which at what distance? At 125. 125. If you simplify this, okay, we will get 375 f. We'll get 375 f. Same way, okay, MB minimum, which is equal to minus f into, okay, minus f into at what distance? Okay, same distance, okay, which is 125, that is equal to minus 125 f. Okay, this is a value. Okay, next for bending load, what is the equation? MBA for bending load. For bending load, okay, MBA is equal to MB max minus MB minimum divided by 2. MB max minus MB minimum divided by 2. If you substitute these values into this equation, okay, you substitute that 375 f, okay, minus here minus, okay, it will become plus into plus 125 f divided by 2, okay, so we will get around 125 f. This is the MBA, okay, sorry, this is the MB, sorry, if you simplify this, we will get 250 f. This is the MBA. This is the MBA. This is will get 250 f. Same way we need to find out MBA. Sorry, M we need to find out is equal to mean stresses, that sigma MB max plus MB minimum divided by 2, okay. So here if you substitute that 375 f minus, okay, 120 c plus here, okay, that's why it will become minus now 125 f divided by 2, now we will get it is 125 f. This is the MBM. For bending stresses, bending stress, okay, sigma BA, okay, that is the equation called MBA divided by ZB, where ZB is nothing but a suction modulus, okay, where ZB is equal to I by C, okay, ZB is equal to I by C, that is equal to pi d to the power 4 divided by 64 into 2 by d or d by 2, okay. So this become this and this will become, okay, likewise 32, okay. So if you write like this, pi by 32 d cube, okay. Same way if you substitute that values, pi by 32 into 13 cube, okay, if you simplify that we will get 215.69 mm cube, okay, 219.69 mm cube, okay. So this is a value we will get it, okay. Same way if you substitute these values into this equation, okay, we know this MBA, okay, which is 250 f divided by what is the ZB, this is a ZB, okay, which is 215.69, okay, we will get 1.1591 f, okay, 1.1591 f if you simplify this equation, okay. Same way if you substitute the values, okay, if you substitute these values, sigma BM, same sigma MBM divided by ZB, okay, we know the value for MBM, which is 125 f divided by 215.69, okay, 215.69, that is equal to 0.5795 f, 0.5795 f, okay. This is a value we will get, and that we all know that sigma minus 1d is equal to sigma minus 1 divided by n minus 1d. Okay, how to find out that sigma minus 1d? Okay, so the sigma minus 1d with respect to this modification factors ESR, ESZ and EL. Okay, EL divided by n. Okay, if you substitute all the values into this equation, okay, this is 275 into 0.8, 3 into 0.85 into 1 divided by the factor of safety, which is 2. Okay, if you simplify this, sigma minus 1d is equal to 97 Newton per mm square. Okay, 97 Newton per mm square. 97 Newton per mm square. Okay, this is a value, okay, with respect to this. Next, what we need to find out? We need to find out the sigma yd with respect to the equation number 1. Sigma yd is equal to what is the formula? Sigma y by n. We know the ultimate stresses which is given in the problem, which is 470 divided by 2. Okay, if you simplify this, we will get 235 Newton per mm square. 235 Newton per mm square. Okay, same way from equation 1, okay, so which is, substitute all the values into this equation. You substitute all the values into this equation. This is the equation number 1. Okay, so now you see here 1.38 into, this is the stress concentration, into 1.1591 F. Okay, 1.191 F divided by 97. Okay, sigma minus 1d. Okay, sigma minus 1d plus sigma bm. How much? Sigma bm is equal to 0.5795 F divided by, what is the value for sigma yd? Sigma yd is equal to 235 is equal to 1. Okay, if you simplify this with respect to F, okay, where F is equal to, okay, we'll get 52.75 newtons, 52.75 newtons, okay, which is upwards, okay, which is counterclockwise. Okay, and okay, what is the value for 3F? 3F is equal to 158.25. okay, 158.25 newtons. Okay, okay, so this is the value. These are the load you can observe. Okay, this is a given problem. Okay, so this is a given problem.